Having seen the power of propositional logic and the limitation of propositional logic, and subsequently we also looked at the motivation for predicate logic. Let us explore predicate logic further. So we saw that statements like some MTech students are active in, say, problem session. Not all MTech students are active in problem session. Statement like this, if you pay attention, you can treat this as simple proposition. One can say this is P and this is Q. It's perfect. One can associate a truth value. That's perfect. But if you pay attention to the statement, there are phrases that is trying to capture something more about the statement. For example, this talks about MTech students. This talks about what is that. In some sense, it's a characteristics, whether they are active in problem session or not active, and this tells you how many are actually contributing to this action or characteristics. Whether all MTech students are active or some are active, at least 2 is active, at most 3 is active. So which means it is not a simple statement, although it is a proposition saying it is denoting P, but can we refine this? Can we refine the variable P or the variable Q to represent something more? Can this variable capture something like this count and students about their characteristics or predicate? So that brings the predicate logic. We saw that there are 2 quantifiers. One is existential quantifier, the other one is universal quantifier. Using these 2, we try capturing the count, whether some is participating, all, or at least 2, at most 2, and so on. Then we also define something called predicate. That predicate will tell us that so and so student is active in problem session, and this comes from something called universe of discourse or the underlying domain. An element in the domain, what property does it satisfy, what characteristic does it satisfy, what predicate does it satisfy. That's precisely what we are trying to represent. So when I say active of X, which means X is active in problem session. Okay. And so the idea is this: given a paragraph or a statement, can you represent them in first order logic or predicate logic, so that maximum information is represented in the notation, or maximum information is represented in this mathematical abstraction. So the idea is to map this to abstract world that will have symbols, notation, and so on. Let's look at a couple of statements. My UOD is a set of MTech students. According to the UOD, the way we write the expression also changes. We define a predicate called active of X, which means X is active during problem session. Okay. Now let's look at a couple of statements, and we will write them using first order logic. Some MTech students are active. I will simply write active, which means they are active during problem session. Okay. So this says some MTech students are active. There exists X. Where is X coming from? X is coming from set of MTech students. And this says some. And we say active of X. Okay. Next statement says all MTech students are active, which means for all X, you can also use different variable. For all Y, which means Y comes from the UOD, it is active of Y. Okay. So this says for each, for all, for every, for any, and element comes from universe of discourse. After picking the element, Y is a student, Y is an MTech student. What property does Y satisfy? This says Y is active during problem session. Okay. Not all MTech students are active. It says not all MTech students are active. Please note, this we know how to represent. We know that for all X, active of X represents this part. Now it says not all. So simply negate this. This says not all MTech students are active. Equivalently, this is equivalent to saying, you can look at it this way. Not all MTech students are active, right? Which means there exists an MTech student who is not active. So it says not all students are active. Let's assume you have a class of 10 students and it tells you that not all are active. Look at first student, you may be active, may not be. But it is the case that not all are active, which means you find at least one who is not active. You find at least one who is not active. Equivalently, at least one MTech student is not active. So at least one MTech student is not active, and they are all equivalent. Writing this is equivalent to writing this, equivalent to writing this. Now how do we write this? There exists an MTech student who is not active. So there exists X, negation, active of X. At least one MTech student is not active. Same. There exists X, negation, active of X. So what is this telling us? Because these statements are equivalent, notation wise they must be same. Writing this is equivalent to writing there exists X, negation, active of X. Okay. So this is telling you a larger message. If you have for all X, active of X, and if you take the negation, what happens when this, if you focus on this part, when you negate for all, the quantifier flips. For all becomes there exist and negation comes inside. I'll either you write here or here, it doesn't matter, with parenthesis. So negation is associated with this predicate. That's it. So now when you negate for all becomes there exist, and negation comes inside the parenthesis. Okay, and it's equivalent. So when you have a negation, when you take the negation outside, what happens? There exists becomes for all, and negation comes here. And these two statements are equivalent. Fine. Consider this statement. None of MTech students are active. So how do we write this? It says none of the MTech students are active. So if you take any student, you see that he is not active. That's what this says, right? None. So for all x, negation active of x. You can rewrite this. None of the MTech students are active. Equivalently, no MTech student is active. You take any student, he is not active. You take any student, he is not active. So for all x, negation active of x. Fine. Equivalently, you see that there exists an MTech student who is active is false. It is not the case, they are all equivalent. It is not the case that there exists an active MTech student, an MTech student who is active. Okay, I'm just writing like this. It is not the case that there exists an active MTech student. Now this means this, they're all equivalent. Okay. There exists an MTech student who is active is false. How do you write there exists an MTech student who is active? Like this. That there exists a student who is active is false. So writing this is equivalent to writing this. There exists an active student is this. It is not the case, so you get negation. Fine. So again, if you see that, if you take negation as we observed before, quantifier flips and negation comes inside. Similarly, when you bring the negation out, the quantifier flips and negation comes outside. Fine. So this captures everything. So this gives you a larger message. You have UOD, it could be set of students, okay, it contains some elements, so x1, x2 and so on. And you have a predicate P, and when I say P of x, x satisfies P. Okay, that P could be he is a good student, he is an active student, bad student, and his CGPA is good, hard working student. It could be anything. In general, you have a property P or a predicate P, X satisfies P. Fine. So you can write like this. So some objects satisfy P. How do we write this? There exists X, P of X. All objects satisfy this, then for all X, P of X. None of the objects satisfy. None satisfy means for all X, negation P of X. Okay. Equivalently, some satisfy is false, meaning there exists X P of X is false. At least one X satisfy property P is false. Okay. And then you get to see that at least one satisfy P is false. So they're all one and the same. Okay. Next one, not all satisfy P. How do we write this? All satisfy P is this, not all satisfy is this. Equivalently, some do not satisfy P. Some do not satisfy P meaning there exists X negation P of X. And as observed, we saw that for all X P of X, if you take the negation, it is equivalent to there exists X negation P of X, or biconditional, they are equivalent. And similarly, negation there exists X P of X is equivalent to writing for all X negation P of X. And in a context, if you find this, you can always replace with this. In a context, you find this, you can always replace with this because they are equivalent. Fine. So with this case study and the predicate, we have seen all combinations in which for all and there exist either appear with the predicate as it is or with the negation of that. Okay. And now once you master this, you just have to define, given a context or an argument, you just have to define appropriate predicate. Once appropriate predicate is done, and if you identify whether the quantifier used in that line is it for all or some, whether it is used in true form or in negated form, then writing an expression is kind of straightforward. And you can also ask whether a given argument is true by employing well-known implications and equivalences. We shall take up such case studies now.